Domain and range is a tool that gives you a snapshot of where you will find a specific relation. So the domain tells you where or what your x values can be, and the range tells you what your y values can be. So for example, I might say your range, the y values have to be above 5. So if you look anywhere below 5, you will not find anything there except empty space. So it's kind of taking your x and y axis, which can go on forever, and it's narrowing it in so that you know where you will find some sort of relation, whether it's a line or a parabola or something you haven't seen yet. Now, before we can actually practice domain and range and how to write it out, we need to remember a few things about the number system and symbols that are used. So for any real number, so whether it's positive or negative, a fraction or a run-on decimal, or anything like that, real numbers use the letter R. And then integers, which are all your positive and negative whole numbers, and 0, that is the letter Z. Okay, so the first two examples are just a set of coordinates. Now, your domain is all about the x's, so I'm going to highlight my x's, 3, 5, 8, and 2. Now, there's no pattern to them, so my domain is really just D for domain. I open a set of curvy brackets and I just write out my values for x. X equals, and I always go from lowest to highest, so it can be 2, 3, 5, or 8. And that's it. And then when I look at my range, again, I'm going to highlight, I have 5, -1, 2, and -3. Again, I will just list them out, and I'm going to use R for range, and range is about the y coordinate, so y can equal -3, -1, 2, and 5. I'm just going in order from lowest to highest number. And that would be it for this set of ordered pairs. Now, sometimes in your ordered pairs, there might be a pattern. So for example, it's all the values from -5 to 10, all the whole numbers, and you can represented in a different way, and we'll see that in the next example. So for the next example, the x values are -2, -1, 0, 1, 2, 3. So it's every single number from -2 to 3. And if you'd like, you can just write them all out like we did for A. Or a more efficient way for the domain is you pretty much just want to say x is any integer. So any whole number, whether it's positive or negative, from -2 to 3. So the way we can write that is x is an element of integers. So the z is integers, and this e means element of. So x is an element of integers, or x belongs to all integers. Then we put this straight line that means such that, or it means something like except it has to follow this criteria. And the criteria is that x has to be greater than or equal to -2, but less than or equal to 3. So whenever I have this kind of double restriction, a lowest value and a highest value, I always put my x in the middle, and then I read it from there. X is greater than or equal to -2, so the mouth or the bigger side of my inequality sign goes towards x because x is greater than -2. And then x is less than 3, so the little pointy part is towards x because x is the smaller one here. X is less than 3. And now I can look at my range. So for my range, my y values are 4, 5, 6, 7, 8, 9. Again, they're consecutive numbers. It's all the integers from 4 to 9. So I can write R for range. Y is an element of integers, except y is greater than or equal to 4, but less than or equal to 9. So I just gave the reader a snapshot. Here's where you will find these random coordinates. And this is when you're just given a set of ordered pairs. If we look at the ones below, they're all graphs. So it's nice because it's a bit more visual. And we'll practice domain and range for these ones now. So for C, it's just a set of points. Now, because it's a set of points, again, it's going to be about integers here. And I can see, just going to highlight for my range, I'm going as low as -3 and as high as positive 2. So for my domain, x is an element of integers because I can't have the decimals in between, and x has to be greater than or equal to -3, but less than or equal to 2. Now for my range, the highest it can go is right here, which is 1, 2, 3, 4. And the lowest it can go is -1. So now I can write that out. Y is an element of integers such that y has to be greater than or equal to -1 or less than or equal to 4. And in all of these examples, I'm saying that x or y can also be equal to that end point because the circles are, or the points are closed. If it had been an open circle, then that value doesn't actually exist. And we'll see that in another example. All right, for D, I noticed that this graph or this relation kind of extends forever. So this point here, it goes on forever upwards and goes on forever downwards. So that really means for your y values, you don't have any restrictions. It just goes all the way to infinity and all the way down to -infinity. And that's the same thing for the domain as well. It might not look at it, but if you pretend that you're zooming out a lot, you will notice that the right side of this graph will continue forever in that positive direction, and the left side will continue forever in the negative direction. It would just take a little, it'll be a bit slower because the line looks almost vertical, but it's not. It will continue that way. So that means we don't have any restrictions on our domain and range. So it can be any real number. It can be decimals, it can be fractions, it can be irrational numbers, or it can be the regular whole numbers. So our domain is just x is an element of all real numbers, no restriction. And our range is y is an element of all real numbers, and again, no restriction. It spans forever. Now, let's go on to E. So for E, we see those arrows again, meaning that this part will go down forever and this part will go up forever. Now, if we look at our other arrows, it kind of is tapering off here. It's approaching the x-axis, but never actually hits it. And same with the left side. So these actually create special lines, and they are called asymptotes. I'm just gonna write that. And asymptotes are lines that your relation approaches, but never touches or passes through. So in this case, we have an asymptote right on the x-axis, and that equation is the y equals 0 horizontal line. And if you look at our graph, the arrows that are continuing forever up and down, they actually turn pretty much vertical. So we have an asymptote right here as well at x equals -2, because remember, a vertical line has the equation x equals. So this is pretty much telling us that our relation can be absolutely anywhere, except x will never be -2 and y will never be 0. So that becomes our restriction. We don't have to give a range of x has to be greater than -2 but less than -2 for the other side. We can say it like that if we'd like to, but it's a lot easier to say x can be any real number, except x cannot equal -2. And that's just a more efficient way of saying it. So for the range, if you wanted to, you could say y has to be greater than 0 or y has to be less than 0. But the more efficient way is y is an element of all real numbers such that y cannot equal 0 because of the asymptotes. Now, our next one is a circle. So you can clearly see where this relation stops. So for x, it's anywhere between 0 and 4. And for the y's, again, 0 is the lowest and 4 is the highest. So we can go ahead and write our domain and range, and we will have that double restriction. So x can be any real number because that line is continuous, or that curve is continuous, except x has to be greater than or equal to 0, but less than or equal to 4. And exact same thing for the range. y is an element of all real numbers such that y is greater than or equal to 0, but less than or equal to 4. All right, let's try another example. And in this example, I have an open hole, and I actually have two pieces to this relation. So let's look at our domain. I see my arrow here, which is telling me that this is going to go on forever to negative infinity. But I'm just going to follow this curve. So all of these x values are okay up to 2, but not including 2 because of that hole. And then after that, I take a little break and I jump to 3 on the x-axis, and then I go on forever. So for my domain, I'm saying x can be anything less than 2, but not equal to it, and then anything greater or equal to 3. So let's see how we would write that. So D for domain. X is an element of all real numbers because of those continuous curves. X is, I don't have that double restriction, that's why I'm starting with x. I just have two separate segments. X is less than 2. Notice I did not put equal to 2 because of that open hole, comma, which just means or, x is greater than or equal to 3. Now, do not put a double restriction. I don't want to see this. X is less than 2, greater than or equal to 3, because that doesn't make sense. If you write something like this, you're saying at the same time, x has to be less than 2, but greater than 3, which is impossible. So that is no. They are two separate segments, so two separate restrictions. Now, let's look at our range. For the range, I can see that my lowest point is at -8. And then if I follow the segments, this segment here goes and stops at +8. But if I just look on the left, this will take me up forever to positive infinity. And so will this segment here. So just because this portion here stopped at 8, that will not be a restriction, because on the left and right, I have extension pieces that go up forever. So the only restriction I have on my range is that y has to be greater than or equal to -8. So range. Y is an element of all real numbers such that y is greater than or equal to -8, and it's equal to -8 because it is a closed hole or a closed point at -8. And let's try our last one. Here for my domain, I see that my arrows go on forever, to the right, to the left. So there is absolutely no restriction on the domain. My domain is just x is an element of all real numbers. But for my range, if I look at it, the lowest point I can be at is right here at -2, but then the arrows take me up forever. So I just have a single restriction. So y is an element of all real numbers, but y has to be greater than or equal to -2. Now you might not see that point as a closed point, but it is because you don't see that open hole. So you can assume that any point on those lines of that V, they are closed, they are contained. And that is domain and range. It is giving us a snapshot of where we will find some sort of relation somewhere on our Cartesian grid.